Good evening. My name is Juan Pablo Cabrera, and I'll be presenting my movie analysis. So, Tom and Jerry, the beloved cartoon, right? I don't know if you guys have seen the movie, The Fast and the Furry, but this was one of my favorite movies growing up. I loved it. Loved the racing. In this movie, there were crazy stunts. As you can see, this is called the Wall of Death. I'm sure we've all heard of it. Car drives around in a big old circle, right? How this works is you see Tom, he's doing the same thing, but I don't know, that doesn't look very circular like. And on top of that, as you can see, this is ice. That's a real big if. I don't know if he can do that. So let's see how centripetal motion works, right? As you're spinning, that means you're changing your velocity because there's a change in direction. Velocity is a vector. Change in vector means a change in velocity. Change in velocity, that means there's acceleration, meaning there's a force, right? So here in this scenario, we have the tension, that would be the force. But in the wall of death scenario, we have a normal force. With that normal force comes a friction force. That's what we're looking for here. So what we're trying to figure out is, can Tom do it? Can he do it? And what does it take? By that, I mean, what kind of radius would it take and how fast would he have to go for there to be enough friction force to support him and make the stunt possible? So we have to do this by 3 steps. One, we find the forces. So this would be like the friction force, like I mentioned, the normal force, that's a big part of it. I'm also gonna take into account drag. Drag is a big part of it, especially in Antarctica with some high density air. Step 2, that would be the max velocity, right? The car has limitations. It can't go infinitely fast. So we gotta figure out how Tom is limited and how fast he can go. And then bing, bang, boom, we have the radius that he can go at. So as you can see from this coefficient of friction graph, right? If we look at Tom, he has studded like spikes on his wheels, right? So this friction graph focuses on studded wheels. And around here, you could see studded wheels on compact ice, right? It has about like a 4.1 coefficient of friction. Luckily for us, Tom is driving on an ice shelf, an Antarctic ice shelf. And what that means is that it's not regular compact ice like here, like it's focused on this graph. Instead, there's some impurities and some granules that allow there to be higher friction. So with that, you can make a reasonable assumption to bump the coefficient of friction up. So for my paper, I decided to go with a 0.46 coefficient of friction. Now, as you can see, we can find the forces, right? From this free body diagram, you see the friction force must equal the gravity force, so the weight of the car. And then you can see the centripetal force right here, the one's pointing towards the center, right? This would be the normal force, which is the important one, because this determines the friction force. So you have the normal force, but then you also have some lift here. Now this lift is due to the car. The car's geometry causes some lift. And this honestly does not help Tom, right? So since we have more centripetal force and this lift force kind of offloads some of the work that the normal force would be doing, that means that there needs to be even more centripetal force for the normal force and to create the same amount of friction, right? So that means either Tom has to go faster or the radius has to be tighter. Okay, so that now we isolated the forces, let's kind of estimate the max speed of the car, right? If you take a look, this is Tom's car. You can see him right here. He just built it. And then this is a 2005 Dodge Charger. That is the estimate, the real life analysis that we're doing. We're doing it on the Charger in order to model Tom's car, right? And I feel like this is a reasonable look, right? You see, this is an American muscle car. This is also an American muscle car. They have very boxy builds, similar builds. So because of that, we're gonna model Tom's car as a 2005 Dodge Charger. Now, using this equation right here, this is the drag equation, but it's the power equation, right? So this considers power and not force. And then with this equation, we're gonna look at the max horsepower of the 2005 Dodge Charger, and then we should be able to find a velocity considering the air density and the frontal surface area of Antarctica and of Tom's car. So with that, the max velocity was 124 miles an hour in Antarctica, which is a little lower than it could have been if it was maybe somewhere with a lower air density. It could have been like around 134. That's an average, but it's a little slower because it is in Antarctica with higher air density. So we're going with 124 miles per hour. This is max speed. All right, now with that max speed, we can plug it into this radius equation, which I derive in my paper due to looking at using the free body diagram I showed before. And then you could plug in the velocity here and then get a radius, the smallest or the biggest radius that we can have to most mimic the scene that we saw, right? We saw that wall wasn't very curved, but the biggest radius that Tom could possibly go in order to stay on the wall at this max speed of 124 miles per hour would be a 138 meter radius wall. So for a little perspective, I put here, you can see that red circle. It's 134 meters in radius. And then I don't know if you can see there's this tiny circle right here. That would be Tom's car. So this circle with this diameter will be Tom's car. This circle will be the wall. That's just how it would look. So yeah, thank you.